Just because one shares doesn't mean one shares and shares alike. And so there are many covalent bonds in which electrons are not shared equally between the two atoms. These are called polar covalent bonds. And polar covalent bonds are important because much of the reactivity in organic chemistry comes from atoms either having an excess of electrons that they are willing to share, or not having enough electrons, still having an octet, but sharing in such a way that that octet isn't shared equally, where they say to their neighbor, like the oxygen and carbon dioxide, well, you're sharing with me, but I don't feel satisfied. I kind of have 8, but I really don't have it because you're hogging it. And this type of unequal sharing gives rise to a lot of reactivity in organic chemistry. I'll take a simple molecule, one that you've seen in general chemistry, for starters. Hydrogen fluoride. So hydrogen fluoride involves electrons shared between two atoms with very unequal desires for the electrons. Fluorine is a lot more electronegative than hydrogen. Electronegativity is a measure of how much atoms want electrons. Fluorine has an electronegativity of 4.0. It's the most electronegative element in the periodic table. Hydrogen has an electronegativity of 2.2. The net result is that even though the fluorine and the hydrogen are sharing the electrons in the covalent bond between the fluorine and the hydrogen, the electrons in the bond are spending more time near fluorine. This in turn leads to a partial negative charge on fluorine and a partial positive charge on hydrogen. And we can designate that HF with a delta positive and a delta negative. Delta means partial charge, so it means that we don't have a whole negative charge. We have a little bit more negative charge in one, a little bit more positive charge in the other. And this is the reason why when you dissolve an acid like hydrofluoric acid in water or hydrochloric acid, you get a proton, H+, and fluorine, F-, rather than, say, the reverse. I'm going to talk next time more about electronegativities, but I want to give you one little take-home message just to maybe get us started on thinking about this. So electronegativity is important. And it's a good measure of whether you're going to have a polar covalent bond or an ionic bond. I'll give you a general rule of thumb. Polar covalent bonds generally have electronegativity differences of less than about 2. I'll just abbreviate that, electronegativity differences. And I'm going to deliberately be a little vague, about 2, depending on the circumstances, 1.5. Electronegativity is actually kind of a crude measure of how much atoms want electrons, because it depends a little on context. We say that the electronegativity of carbon is 2.5, but depending on the hybridization, whether it's sp3 or sp2 or sp, there are actually some differences. That's why I'm being a little vague here. And then the flip side is ionic bonds generally have electronegativity differences of greater than about 2. And again, I'm sort of vague. I'll say greater than about 2, but again, maybe we can say 1.5. And the final point that I'm going to leave us on is that nonpolar bonds. So how much electronegativity do we have to say it's polar? If it's less than about half a unit of difference, we would probably say it's nonpolar. So a nonpolar bond, and I'll put that in quotes because of course there might be a little bit of polarity. A nonpolar covalent bond, we'll say less than, and again I'm going to be a little bit vague on this, less than about 0.5. So carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.2. That's a very small difference. We would describe that as a nonpolar bond. All right, we will pick up next.